mechanistic model is wrong because our mechanistic model is really a simplified and frozen partial description of reality, of some piece of reality. We've made simplifying assumptions, and our model is only the dynamics of average types, average molecules, average, etc., interacting through average processes. So a lot of economics, obviously, is about basically averages, average people, average this, that, and the other. And the dynamics is too. But of course, fluctuations in density and parameters can lead to self-organizing spatial and temporal structures. Whenever you have feedback loops of interaction presence, and you do all over the place, then fluctuations can tip it into new regimes which have new properties. And on top of that, microdiversity, the fact that the individual elements that are underneath the system are different from each other, that gives you adaptive self-restoring capacities as any decline takes out the vulnerable and leaves the less vulnerable. So in a way, you have a system, evolution is an automatic process almost that you can't avoid, because that's what it does. So you end up with things that survived until then. Any ecology is made up of populations whose microdiversity deals with changes from other populations or the environment. So in other words, if you have an ecology, an ecosystem, and it's reasonably, and it's stable, then it's because the microdiversity of different species fit each other, if you like. So although you get occasional waves, the point about it is you cannot know in advance what microdiversity will be needed for the next bump, if you see what I mean. So the point is that when I started this, I remember somebody saying, oh yes, so you can work out what mutant you need or something, or what new behavior you would need. But the answer is that you can't, because you don't know what the problems will be, and you don't know how the system is moving on. So microdiversity will be needed, but you don't know what precisely, which bit of diversity will be needed. So I then started to develop this sort of picture of understanding real problems. And so in reality, I've drawn it as a cloud. Reality and practice is a cloud, and it's a very soft system. And in a way, there are no hard, fast rules, no beautiful, pretty equations that you can get out of that. Oh, no, wait a minute. So why did it do that? Oh, wait a minute. Oh, there we go. So that's the next one. Okay. So what we do is we take some piece of reality and we build a model. And actually just the first step is to look over what that system has been through time, if you can, and you can see that it starts off as one thing and goes through changes. There are new things appear, and finally, at the time you're looking at it, at the end, you've got X, Y's, and Z's have survived and are running there, and you're going to build then next. Your next feat of understanding will be to build a model of X, Y, and Z interacting. But the initial model is evolutionary and started without necessarily X, Y, or Z, and came through qualitative changes to the present. Now, when you want to know, yes, but I want to know what X, Y, and Z are going to do, or what I should do about them. So you take a model that uses the definitions of X, Y, and Z variables. And of course, it is initially probabilistic, and it's probabilistic nonlinear dynamics. So the point is that can have structural stabilities and fixed variables. And so out of a model like that, which still allows for individual micro variation and things like that, you can have stationarity as a possibility. And people have applied it to problems of sand piles and rank size rules in urban systems and cities and firms. But if you say yes, but it's still very wobbly, it's not giving me clear answers. So let's have a clearer answer. And so what we do is we move. I don't know if the arrows show up or not, but anyway, probably. Anyway, so we move now to the average dynamics of X, Y, and Z, and we can build systems models. So this was systems modeling. This is what it's based on, that set of steps. And you can, and of course, many people, particularly in economics, went one step further and said, well, gosh, it's awfully difficult. Look at this dynamic model where things are changing. My God, let's look at the stationary, let's look at the equilibrium answer to those equations. And so most of economics was about equilibrium, or assumed equilibrium as a first step, actually. So the question you can ask yourself is, of course, for the long term, we're interested in strategy. For the shorter dynamic version, we're looking at contingency. And for the system dynamics model, you build them very often for operational questions. And of course, complexity sits with evolution, in the sense complexity is about the rich system that gives rise to the appearance of simple systems. And you can ask yourself, I put a question mark under the, as you go through this process, are you understanding things better, or are you actually hiding the complexity in a set of assumptions of whose consequences you don't really know the answer? So the question is understanding question mark. So complexity sits there. That's the short term is about the system dynamics, if you like. The medium term is the probabilistic system dynamics, and the long term is the strategic changes and structural changes that can occur to the whole ecosystem or to parts of it. And so this is where Prigogine wrote the book called From Being to Becoming, where he talked about the fact that science had for a long time been about equilibrium, if that had been about being, and he was trying to move towards becoming, which is how things go in reality, what creates the universe and the earth and all the animals and humans on it. Okay, so I thought a long time ago of this, I think, superb example of the issues that we're faced as scientists when we look at a problem. Now, if you know enough about origami, then origami is just about folding paper, right? But folding a paper is a way of breaking symmetry. So if you have a flat piece of paper and you fold it in two, you've broken the symmetry of that. And the point is that by folding a certain sequence and a certain number of folds, you can come out with all these different things which have emergent features, emergent variables, emergent dimensions, emergent functionalities. So these things, the vase could actually hold flowers, you see. The bird could fly, possibly. But the point about all that is that physics, hard science, only deals with the paper. It doesn't know anything about these forms that can be created. And what matters in the real world is the emergent forms that are in interaction, all the different species, the different activities, and so on. So in a way, physics is too microscopic, if you like, to look at this bigger picture. Okay, so and the point about this is that an origamist who's finding how to make a seagull, etc., he selects on the basis of the emergent properties of the folded paper. But that's exactly what the world does. The emergent properties of folded molecules is biology, the emergent properties. So the point is that, if you like, the physics of that is, I mean, obviously not trivial, but it's not the point, because the real issue is the emergent properties that can appear at a level above molecules and so on and so forth. And that's what's important. Folds and forms means emergent capabilities, and symmetry breaking is very, very important and profound. So if you look at the old models that people used to do, you'll find that they don't involve symmetry breaking, because it introduces new dimensions and new issues. So innovation in reality is about symmetry breaking, proper innovation, but that's in a way excluded from most economic models. It used to be. Okay, so since 1970, when I was doing all this, I had two good ideas, only two, but that's three more than average, you see. So that's not bad. Evolution occurs through structural instabilities, unintentional and intentional novel actions, experiments caused by internal heterogeneity, microdiversity, ignorance, emotional error. So in other words, evolution occurs through an exploration process of forms. And the question is, to what experiments is the system unstable? Which new actions, mutants, innovations, or practices will grow in the system if they occur? That's the question. What will grow in this system if they occur? So you've got a double thing. Will they occur? And if they occurred, would they be stamped out, or would they grow? So that's and the second thing is for an innovation to persist. So if some change occurred, its components must together possess an emergent capability. So they must be able to do something that is useful, if you like, to themselves. The environment of the subsystem must reward this capability, then it will grow. This is the definition of synergy, the second law, or economic value. Right, so these are my two basic ideas, and I then applied it repeatedly. I don't know what, I applied it a lot, and in particular moved on to spatial models, urban models, and so on and so forth. Different types of actor in each zone with characteristics needs to be fulfilled. The characteristic needs are stable, but the behavior of actors depends on the changing circumstance. So I didn't really, in those early models, think about people learning, changing what they want as time went on, or as things. So it was really just about spatial distributions of different kinds of activity, different kinds of people, and which affects where jobs are, and potential for housing, commercial activities, and all that. So that was what I built. And of course, transportation and land use decisions should be put within such a context in reality in order to see what the consequences might be of a given action. So I wrote this splendid book, absolutely super, slightly out of date, unbiased opinion, there you are, an excellent book. And so that was all summed up in that. The work continued, and I had colleagues, Guy Englund and Roger White, who went on building models on fine-grained spatial processes with changing transportation costs. And so they were using cellular automata, and it was a lovely dynamic issue. And in fact, if we show, this is Dublin, I think, that they did. And if you look at it, the year is changing on the top left-hand corner. So it's actually showing you the urban developments that model was predicting. And you could run it many times, and you could hit it a bit or add fluctuations to show how stable different types of progress appeared to be. So that was where I got to at that time. I then applied it to all sorts of things, putting new road into Bengal, investment in Nepal. I worked for a long time with Canadian fisheries on fishing boat behaviour. and fish behaviour and everything, which was extremely interesting. Of course, Darwin's finches, if you know anything about Darwin, then he was, I mean, puzzled or interested by the Galapagos Islands and the diversity of finches on different islands. And so you can build a model now which looks at the diversity you would expect. I did the Rhone Valley, which was about stuff coming down the Rhone and polluting the Mediterranean. I did a Greek area where it had agricultural production, etc., etc. The same thing in Spain, where there are water problems. In Senegal, I did a whole model of Senegal. And Guy England and Roger Wright did Puerto Rico. And so you can see, again, it's running, and it's actually, you're showing urban development as the model would predict. And then I did other ones on UK electricity, spatial pattern of where it would be produced and consumed and so on. So all that's lovely. So you come that I'd moved across to modeling social systems, basically. And I was interested in multi-agent models, and this seemed the way to go. Do you know, but the question, of course, is, do you know what agents are trying to do? We can ask them what they're trying to do, but of course, in reality, they may not reveal, or they may not have any real thoughts, and they might even lie. So one of the problems of social systems is people are complex themselves, and they have multiple levels at which they'll answer your questions. And reflexivity is a really important thing. The agent's own feelings, reactions, and motives, and these influence what they do or think. So in fact, we need multi-agent models that can put together the, I can't see what that is, anyway, it's behind, doesn't matter, can put together things, and the powers of different agents present, or the aims and powers of different agents present, put them together and learn. But of course, when you do that, you start to introduce the possibility of lying among the agents and copying. So even if agents are honest, when the model's results are discussed, people may change their behaviors. They experiment, reflect, and model. So in other words, because people are alive, they may well change their behavior in the light of what's been happening and what other people are doing, and so on and so forth. So this is a very, very complex model. So here's my here's a framework which shows why all this destroys predictability for social systems. So I've got Plato's cave on the one hand and data and statistics, but here I am, here's the modeler, here he is, and I'm saying, look, there's all these people doing these things in this city. I need to study them, and then I can build a model which puts together what it is they're doing, and with data and all this, I can put it together, and I can build a model. And at some point, maybe there's the model. At some point, though, the players in the system might also be able to see the model. So it's whether you should have urban models which are anonymous and hidden, or whether people could access them and see what the model was saying about them or assuming about them. And of course, if you do that, then it feeds back to the people being modeled, who then think about what it's telling them and may well change their behaviors. So what you have now is the fact that the model is part of the whole system and is responsible in some ways for it changing. It affects the changes that occur. So reflexivity can invalidate any model. So if you make a model about people's behavior, then if they know about it, they may reflect on what you're telling them and change their behavior. and that they may, looking at other people, they might do it, or they might. So agent models are just part of the system, and the whole thing will evolve and can evolve. Right, so now I come down to this very handsome picture of my head. It says my skull. I can't quite see it on mine, but anyway, so this dotted line is my skull. I'll do it with this, yeah, dotted line, my skull. And inside my, well, of course, I've got the world outside, and everything I do is really an experiment. I take action, or I do something. And of course, what happens is noisy and probabilistic. So the world replies or does something, and I get an answer, so to speak, which either deny or confirm my expectations. Now, if they confirm them, then I continue up this road here. My ideas are confirmed, aims and goals and values confirmed, decision and choice, and so I go around. So I will stay in that circle for as long as my expectations are not denied by reality. Now, that's science, you might say, but of course, once they're denied, once it doesn't work, I thought it would do this, but it did that, then I have to work out what's wrong with my model. And so that's about the beliefs that underlie my model and the knowledge I think I have. And I have to modify it. But this is not a scientific process. There is not a scientific way of doing this. You basically think, oh, I know, I think it's that. I think I've missed that. So you try it out, and if it gets worse, then you say, oh no, it wasn't that. Anyway, so you see what I mean, is that really the whole of our beliefs are built up by repeated experimentation of living. And we hope that we find a workable answer. So, as I say, if you, when it confirms what you thought, then you carry on. When it doesn't, then you have to modify what you think, and there's no science of how to do that. And so basically the question then is, do our experiments stabilize or destabilize our understanding? That's the question. Right. And what is my aim? Is it good for me, or is it good for my community? Are we honest scientists? Are we in denial? Are we hierarchical sheep? So in other words, am I an honest scientist trying to answer some question to find out? Am I a pig-headed person of whom there are a few who say, I'm not wrong? Loss of faith, my God, insecurity, pig-headed. So in fact, people react quite differently to being told that they've made the wrong answer. And of course, and I was doing a lot of work in early China in those days. So you actually had to have the other alternative where people said, oh, but what do you think, master? So in other words, hierarchy and power in some societies is totally dominant. Whereas I think in most European societies, that's not the case anymore. So inside my skull, all these things can be going on. And the question then is, of course, we've had personalities. So the question is, am I an honest scientist? Am I not wrong? Or am I simply looking for what my master wants to be true? And so all these things lead in the end to, if you take economics, then you get groups of people. All these are all separate brains, you see. So these are all separate people, and they form groups. Oh, I'm a Schumpeterian, or I'm a pragmatist, I'm a flat earther, or I'm a neoclassical economist, and so on. So basically, and then they all agree with their group. That's why they're in the group, and they So the whole thing forms up, and everyone passes their time writing papers about their own ideas and other people's ideas, how they're wrong. And there's a retention of successful group identities and ethical behavior, basically. So, right, so I'm doing very well, actually. Yes. So this moves us on to the fact that, as you can see, when you build proper dynamic, evolving models of human behavior, you come up to something which this psychiatrist McGilchrist has written about, and he's a little bit too enthusiastic initially, but essentially he thought that the split brain gave rise, you see, because what our modeling is telling us is that we need to have deterministic processes, which is our model when it works, but we need, in order to deal with it when it doesn't work, we have to have some other process ready to come in. And so whilst the left brain was suggested was about logic and sequencing, linear thinking, mathematics, fact, thinking in words, the right brain, it was supposed, was imagination, holistic thinking, intuition, art, rhythm, non-verbal cues, feelings, visualization, and daydreaming. So, in fact, when I said, you see, there is not a definite process by which you can update and change your ideas if they don't work, then this is what McGilchrist is answering with his how evolution has shaped our brain. So the ideas of McGilchrist are that we have a brain that's evolved to be rational on the left side, but to be able to go on with the right side, looking at new things or thinking differently or whatever. But this, so we have to have, because we have to have the rational and the exploratory side present in order to survive evolution, if you like, and the evolution of systems that we've built, that we're part of, and so on. And of course, so if I go back to my purely mechanical models, I started off, oh dear, wait a minute, I started off from, we see that they were wrong because they're a step back from our brain because they don't have the imagination part in them. And in fact, when I look back at the early work I did on urban modeling, I find that, well, it was all very clever and it worked for some years, but in fact, the meaning of the variables all changed. So in fact, we're having workers, industrial workers and office workers, and was this the correct splitting? And of course, there were no computer workers at that time. So all of these, so in other words, the system's actually evolving qualitatively as well. So our mechanical model has severe limits to it. And that's in a way what I've been exploring here. So conclusions. Models really are for, in social science, are for learning, not prediction. You develop models to explore possible futures. Models are needed to explore possible designs and changing circumstances in order to imagine possible futures. The models are not just describing past statistics and events, but because of noise and randomness and interactions, you can tell us possible futures that we didn't know, hadn't thought of, and weren't in the data. So in other words, once you're put into models, the possibility fluctuations and variation and so on, then you open the opportunity of finding new situations and requiring new thoughts. When agents, so reflexivity, when agents see the outcomes predicted by the model, they may modify their behavior. So modeling is actually also about you changing, or if you're part of the model, changing your behavior, which would then invalidate the model, of course. But this is really called learning, and it might be the aim of such modeling. And you can imagine a Machiavellian version, which would actually encourage, try and make people learn the wrong things. I suspect the advertising industry is well into the Machiavellian version. The model could also help develop empathy, understanding, and community. It could help the region forge its own sustainability. So when people understand and they discuss, then this could help them survive, basically. Now, finishing with the following, complexities life. So each region where we live has its particular history, characteristics, and situation. Models can help us understand its past and reveal choices and dangers, and thereby change the future. In a complex world, everything is an experiment, and we shall need to continue experimenting. So in other words, in a complex world, we never know that things will carry on as they are. We never know that. So we have to be aware that we may need to experiment. Now, the second one is, I think, very important. Models do not make predictions, really. They are instruments of reflection. And this key point, they show us when reality is in fact deviating from the model. So you set up a model, and if I talk about my old fishing model or my urban model, early ones, the variables were going wrong. I mean, they were not the right variables. It's deviating from the model and something new is happening. So if you don't have the model, you don't know that something's changing in the system. And of course, most economic models have been purely, how can I say, descriptive, where they take the data and they just modify the data as new data comes in. But the variables are actually, it's an expression of what people are believing and trying to do, of technology and all that. So, and of course, politics and social science needs to frame problems in this integrated way. Enhanced understanding and clearer views of possible futures can become part of our evolving complex world and universe. Okay, that's it. I'm sure there are no questions. Okay, what do I do now?
Thank you very much, Peter. I think we can open the floor to people physically in the room. So if anybody has questions, you can put up your hand and maybe stand up so the speaker could see you.
No questions.
And Deb, if you want to.
Yeah, I do have, well, at least let's start the discussion. So biology, so you're basically talking about complex adaptive systems.
Yes.
And the way biologists deal with it is, at least the first, when you started, the first thoughts that were going through my head was that they have this genotype-phenotype relations, and the phenotype is the one that you are referring to, probably the origami part is like the like an emergent phenomenon or emergent structures from genotype, and the natural selection is then based upon, like, the person who's selecting the origami based on which shapes he or she can form. And that is selected, the special the phenotype is selected by natural selection.
Yeah.
And that has also its feedback onto the genotype selection. And this is, so in order to get a complete picture of the, let's say, of the emergence and the genotype-phenotype relations in that, or to model the full complexity of this complex adaptive system, at least the biological ones, one would like, I mean, I think it is possible. That's exactly what the biologists are doing.
Yeah.
When it comes to human behavior, what you tried to do is that you also brought the models into the fold. And that gave me the feeling that, I mean, take, for example, the behavioral economic side. And if the stock markets become very predictable, then then basically it doesn't exist anymore.
Yeah.
If no one, I mean, not it's like a so I mean, I know that, for example, human behavior is just essentially unpredictable, and that's exactly why stock market functions.
Yeah.
And the question is that, will the rules of the game be known to the players of the game? Because that is your fundamental assumption. Because if you do that, then of course there is, I mean, I don't think any solution is possible. Could you reflect on that?
Well, I when I was reflecting on some of this, it came upon me. I wrote a little paper about it, where the fact that Adam Smith lived 100 years before Darwin, 100 years before Darwin, and he came out with the idea that if commercial activity, or whatever it was performed by Christians who were all honest and so on, then you would end up with the best possible answer for the whole system. Now, Darwin never said that. Darwin was more, so Darwin in a way used the ideas that Adam Smith had said, oh, well, when you get all these things interacting, my God. He never said that what came out of it would be the best. And it's still very important, because many people believe that market systems, by being free-ish, are the best that we can do. And we see other regimes and so on, and we disagree. But in reality, just having free interactions leads to an outcome. It doesn't prove, nobody can show it. Nobody even knows what the measure would be of the best and less good and so on. So in fact, it's quite interesting that Darwin never made that step, which said that if you let the whole thing go, let it run on and evolve, then you would get to the best ecosystem or something. So I think it's very interesting that difference occurred, and Darwin was 100 years after Adam Smith. Adam Smith can't be blamed for, at the time, it's very early. It was quite a remarkable vision, I think, and compared to how trade was carried on before. But anyway, I find this is very interesting, because I was saying I was writing something about the dinosaurs lasted for 135 million years dominating the earth, and we've only dominated it for a few 100,000, if that. And the point is that the collision of the earth with a 15-kilometer rock that hit us destroyed the dinosaurs. They disappeared. They never came back. And we went on to build a totally different ecosystem. And so what I believe people don't face up to is the fact that the outcome is not optimal. It's an outcome, and it's ongoing, and we don't know what the outcome will be anyway in the long, because you can't say when it will end. But I mean, the dinosaurs thought they'd won and done everything, and they were very stable for a long, long time, and then they disappeared. So in reality, I think that these evolutionary thinking tells us that creativity is there and it happens. It's very hard to say what is the best economic situation or anything, but people still carry Adam Smith with them, because they do believe that free markets give the best answer, which is probably not true. They give an answer. What is the best? For whom is it best? The answer is for the winners, but that could have been historically completely different set of people, really. Anyway,
Yeah, I see there are more questions, so I will.
Yeah, okay.
I want to follow this up, but let's give the other first a chance, and I'll come back to it.
Okay. Thanks very much.
So perhaps, yeah, first, would you want to switch on your microphone and ask your question?
Yeah, yeah.
Yes, that's right. Can you hear me?
Yeah.
Yes, yes.
Okay. Well, what I wanted to know is actually in geophysics and reservoir simulations, we do history matching. That means you take data up to a particular point, then you have a model that does prediction.
Yeah.
So you do prediction at that time, and then you can validate that using what is actually later on then produced for a particular reservoir. So if I look at your urban or fishery models, there should be possibility to predict at a particular time what the next stage is going to be, and then you can verify that with what really happened. Have you done that sort of history matching?
Well, that was in a way how I started, you might say, and of course that was the aim of the models, was to. We were doing work for the Department of Transportation, US Department of Transportation, so we were claiming, if you like, that our models would give you the answer. What the models, it's very, because history runs once, but not twice or three times, then it's quite hard to say. And we had the cases where some urban changes were made, and in one case they were very successful, but in another case that looked very similar, they completely failed and everyone went bankrupt and so on. So what I'd say is that models which involve people or claim to represent people are very rich in possibilities, and very often a small initial fluctuation can become a new set of ideas and new thoughts, new understandings can emerge which change the system. Basically, it becomes a different system. Now, this is not, as I imagine, it's less true of the system you were talking about. There may be less kind of imagination available. But of course, fluid mechanics, I know, is a very rich subject in reality, very tricky. And prediction itself is not, hydrodynamics doesn't successfully predict everything, does it? I don't think. So there are limits to how far you can predict. I mean, the course of rivers, you can say, we understand why there are loops and there are lakes that break off from them and so on and so forth. But the actual prediction is pretty dodgy, I think. It's pretty difficult prediction.
Well, what you do in the prediction, actually, you put in there sort of some randomness. So you say whatever randomness you do, because you don't know all the parameters sufficiently well. So you get a range of possibilities equally likely, and you can take the average and then look also at the uncertainty. Now, is that something you've been doing with your models also?
Well, I would say that, yes, obviously, a lot of the models which we built, we ended up, if you like, looking at different possible futures, and some are qualitatively different. In other words, if a town becomes two towns or something, as has happened, or if you put in a new city or something, you can't predict. How can I say that? The predictions are useful, I guess, and it's worth exploring. In that you can spot that there might be some decisions which take you to a small probability of a disastrous response or something. So that's important to know that. But on the whole, I suppose what I'm really saying is that physical systems are less imaginative than human systems, and humans will come up with all sorts of things, and they're extremely intense, loops and self-reinforcing things that can happen in social systems, which physical systems on the whole don't often have.
Okay, I agree indeed
Yeah.
that humans are much more complicated than
Yeah.
oil and gas reservoirs. Right.
Yeah.
Thanks very much.
Thank you. Thank you. Okay. Thank you.
Okay, so next question in the chat was Ong Tong Wu.
Yes, thank you for the nice talk. I was wondering if we look at like for economics from a more biological perspective instead of a physics, I mean modeling perspective, how actually does your talk relate to the Tinbergen's questions on approximate and ultimate causes? I mean, could we tell more about the things if we look at qualitatively instead of, I mean, we only need to know what's happening. I mean, qualitatively instead of really using numbers and the modeling thing, because the model is, yeah. So that was what I was wondering, looking at it more qualitative perspective instead of.
Well, that was the point.
Yeah.
Our models introduced for the first time, as far as I can see, the issue of qualitative change. Whereas they still run urban models. They're totally quantitative. And of course, a lot of economic, totally quantitative. Whereas in reality, what's more important often is the qualitative structures that emerge. So you suddenly get the right wing and the left wing, and they start fighting each other or something. But I mean, the quality structures, and that's what I showed with the origami. I mean, you fold paper, you do 3 folds, you're moving towards a bird. In another one, you're moving towards a vase. And they're qualitatively different. They have different measures of success. They inhabit a different world. They have to fight different problems. So what can start off as, because of nonlinear interactions and reinforcing reactions and so on, human systems certainly, and certainly animals as well, but I mean humans can create entirely new concepts and ideas. I used to talk about the fact that when I was a kid, all motor cars were black. All of them. They painted cars black. That's what they did. And the truth is that suddenly somebody said, hey, I know my dad turned up once to meet me from a camping trip, and he was in a yellow car, and it was so utterly amazing, ridiculous. And of course, so color became one of the dimensions, possibly very important dimension of the sales process of cars. And so in other words, it's not just that, well, opinions get different dimensions added to them or can change. And today we're looking at, here we're worried about carbon problems, obviously heating the planet. This is entirely new, really. I mean, I know that some people have been pointing it out for a long time, but for the bulk of society, it's been completely of no interest whatsoever. They didn't know anything about it. And so consequently, this is the interesting fact that we move from one set of ideas to another. If you look at, and even then they don't make sense, because if we were looking at cars, say, some years ago, they were getting very streamlined and very streamlined. And now they're all bumpy and knobbly and high and everything, because it's ridiculous from fuel consumption point of view and so on and so forth. And yet people go that way. So fashion and advertising, all this can take humans in really strange ways. And obviously, as we see in politics, I mean, it can be disastrous for everybody, and ridiculous, really. That suddenly these things, some things matter that didn't seem to matter before. And so we have a set of measures of things, but they change, the measures change. If we get new measures of what is successful, what do I want? Well, I want something like that. I want it to be light. I want it to, or I want to be heavy. And fashions change for sometimes for good reason, often for not for good reason.
Thank you.
Okay. I don't know if I answered your question.
Yes, certainly. Thank you.
Okay.
So we've 2 more questions
Okay.
and about 5 minutes left. So the first one from Gert Buiten. So if you could switch on the camera and microphone, Gert.
Yes, thank you. Well, my camera is already on.
Okay.
Well, thank you very much. My name is Gert Buiten. I work at the Statistical Office of the Netherlands.
All right.
And I was quite interested in your one of your first slides where you showed that the model can actually become part of reality.
Yes.
I think it is even simpler also that simply statistics on, for instance, unemployment or the inflation rate or the interest rate, etc. They themselves are also influencing the behavior of the agents, and to a certain extent also I think of the system, because when I look at some of our statistics, and things like unemployment and inflation are examples of that, they actually measure some of the emergent properties of a complex system. So you, more or less you have a mirror in which the system can see itself, including its emergent properties, and then you add in this way a new feedback loop. And now I come to my question, because we all are aware of this kind of more or less traditional statistics. Since a couple of years, we're also trying to work out actual statistics on complexity. And 2 examples are a micro network data set that we have been developing on the Dutch population network. And we're also just have a data set on the interfirm consumption network, so to speak.
Right.
So those are 2 new statistical products, and I was wondering if you do you have any ideas of what this new kind of information could do in a feedback loop with the system? What could happen?
Well, yes. I mean, because how can I say, because historically people didn't think about that, then in a way a lot of it didn't happen. Whereas once you've thought of it, I mean, the idea, I forgot what, but where you put firms in a thing and close it and say this is a commercial situation. The point is, if you could put complementary firms who would actually use the input and the output of each other, if you could put them together, that would save such a lot of travel and transport and everything. It'd be really remarkable, and it would probably make them all successful. But the trouble is that the complexity of the real world, who owns this, who's saying this, yes, but I said that, and firms taking over chains of firms and things like that, it's rather difficult to see it clearly happening. Then it may be that the developers of a particular kind of industrial parks or something may try and provoke it so that they get things that want to be together put together. But on the whole, it's not. There's so many other issues, I guess, involved, financial and all that. But it does strike me that we could make complexes which were much more efficient in every way for the environment as well. And in fact, things all went on inside, and then the only things were certain external products that we input shipped in and export shipped out. But that was very, very efficiently handled, really. Whereas the accidents of humans operating freely is, we can discover this because it does happen occasionally, but mostly it doesn't, because there's too many other things happening and people haven't thought of it properly.
Well, thank you very much.
Okay.
Thanks, Kurt. Just for everybody, it's now 1 o'clock, so if you do want to leave, the microphone's off, so please feel free. But if you're okay with it, Peter, we could have one more question.
Okay, yeah, sure, yeah. Okay.
So for everybody that will leave, thank you very much for coming. But Alvaro, I'd invite you to switch on your camera and microphone.
Yes, I'm already active. So I'm doing a master called Bioinformatics and Biocomplexity.
Yeah.
And I always struggle to explain people what the complexity part is about. I had a very interconnected idea of what it is, but I always struggle to find a metaphor or a swallowable pill for layman people. And I really like your analogy of the origami.
Yeah.
So
yeah.
I guess that what you said, physics is the study of the paper, which is the tissue that composes everything. If you make birds out of this paper, then the study of these birds is biology, and how they move their wings and so on. But in this metaphor, what is complexity?
Well, I mean, I suppose that because we get mixed up with linguistic issues, so that complexity, somebody's invented the word, and now we have to work out what it is they're talking about. Now, I think in many cases previously, complicated systems were considered, would have been called complex. But the reality of what we really mean by complex systems now is that they are things which we have internal interactions and feedbacks, and which have opportunities for different possible outcomes and structures. So that a complex system could just be sitting there with everything doing the same thing, but it can also go into different, activities which may turn out to be complementary and so on and so on, but and self-reinforcing or whatever. So in fact, the critical thing is that the whole of biology is the result of that. But science never really, well, I say like origami, the idea that you've got all these things and they actually function, they do things, and they're actually changing the world by eating or drinking or whatever. And I don't think it's ever been, I think all our words are not sufficient. So that we use the word complexity, and now we think we mean systems with nonlinear interactions and so on and so forth, where self-reinforcing can occur and all sorts of things. And because we know now that we know the tricks you have to put into a set of equations to get them to have multiple possible outcomes and so on. But because nature didn't know that. And it's simply, that's why I said the creative universe. Because not only is it clear that if now we're starting to understand much more the history of the universe, and you go from stars had typical forms early on, and then those forms did various things, and so it went. So the stars today are not the stars of yesterday. The original stars, they're different, they have different things. And of course we built up all the elements by having stars that got hotter and hotter, and so in the end they could create elements beyond iron and things like that. But all of that is creative. I mean, it's not known beforehand. And I think the biology is the same. So you start off with things crawling about, and then gradually evolution will take it to having the wonderful things that we have seen. And of course, human beings are sometimes wonderful, sometimes not.
Mhm.
But it's and what we're doing with society. You know, I mean, we don't know the outcome. There isn't, you know, we're doing our best, but it is creative, and we get new problems turning up. I mean, the idea that previously, when we had a despot in power, he didn't have nuclear weapons available. So if you go back through the wars, they were just wars where people killed each other. But now you actually have the possibility that one man could set off something that destroys all humans. That is really quite new, quite new. It probably requires some new international legal system or something to deal with, or something will happen. I don't want to depress anybody, because you're going to have your lunch. So. But
well, we could leave it on that bombshell.
Okay.
Yeah. Well, thank you very much, Peter. We all very much enjoyed it. So yeah, thank you very much.
Thank you. Thank you. Okay.
And yeah, thank you all for joining online as well.
Thank you.
So enjoy your day. Thank you, Peter.
Cheers. Okay. Bye-bye.